Hello friends, today I will discuss the torque slip characteristics of three-phase induction motor. So in this video, it is divided into two parts. One is aim. Under this, torque slip characteristic, effect of rotor resistance on torque slip characteristic. The third one is torque speed characteristic. The last one is motoring mode operation, generator mode operation, braking mode operation of the three-phase induction motor. So to discuss these points, we also use some of the terms, that is squirrel cage induction motor, slip ring induction motor, slip, low slip, high slip, synchronous speed, rotor speed or motor speed or actual speed, which can be measured with the tachometer. And the other one is the torque equation, rotor resistance, rotor reactance, power equation. P is nothing but 2 pi n into T divided by 60. Here n is the rotor speed, T is the torque. And 6 is stable region, unstable region, full load torque, maximum torque, starting torque. The other term is load, torque, speed, relations. Torque equation is nothing but K into S into E2 square divided by R2 square, S square, X2 square. Here S is the slip and E2 is the induced EMF in the rotor under standstill condition. R2 is the rotor resistance per phase. Similarly, X2 is the rotor reactance per phase under standstill conditions. Here we also discuss what is no load and less torque, more speed. Similarly, more load, more torque, less speed. So here, three-phase inductions or motors are the two types. One type is called the squirrel cage three-phase induction motor. This motor will have a fixed resistor for the rotor, that is like this. So this rotor will have the conductors in the form of bars like this, and it is fixed, which cannot be changed. In the squirrel cage three-phase induction motor, this is called the stator and this is called the rotor, with bars as the rotor conductors, which cannot be changed once it is manufactured. And this is the bearing, and this is the end bell. This is also end bell. This is the wiring cover or terminals, and this is the motor frame or yoke. So once all these components are inserted into the stator, this is called stator winding. So then the motor will appear like this. This is the rotor and this is the stator, this is the shaft, and these are the motor terminals to connect supply. So for this type of squirrel cage induction motor, the torque slip characteristic is fixed. Its torque speed characteristic cannot be changed. Only one characteristic can be obtained or will be obtained. Coming to the other type of three-phase induction motor, that is called the three-phase slip ring induction motor. It appears like this. This is the rotor core, this is the rotor shaft, and these are the brushes, and these are the slip rings, and these slip ring terminals are nothing but this. They are nothing but connected via brushes, and that will be connected to a variable three-phase rheostat like this. Once this motor is drawn in the form of circuit, it appears like this. This is the stator. This stator and the squirrel cage induction motor stator will appear same, will be same also. Squirrel cage induction motor stator is like this. The same stator can also be used for the slip ring induction motor. Same stator will be used there. So once it is replaced, the three-phase stator winding which is connected in the delta form is drawn like this, and these terminals will be connected to the three-phase supply. So once three-phase supply is given, means here a rotating magnetic field is going to be developed, and in this stator a rotor is inserted. This rotor will be inserted inside the stator, which is already shown in case of squirrel cage induction motor. So that a rotor winding and circuit can also be drawn like this. For slip ring induction type of motor, the rotor winding is in star connected form like this, and these terminals are connected to the slip rings like this, and this is the brush, and here these are the terminals. These terminals are going to be connected to the variable three phase rheostat like this. So then this is called the slip ring induction motor. So for this type of slip ring induction motor, the torque slip characteristic can be varied. When this rheostat is at 0, there will be a rotor resistance. With that, there will be a one torque slip characteristic. Similarly, once some resistance from the rheostat is introduced into the rotor circuit, then another type of torque slip characteristic will be obtained. Similarly, if the rheostat is further increased its resistance, then another torque slip characteristic is obtained for the slip ring type induction motor. When we look at the three-phase induction motor, in general, it appears like this. So this is the stator which houses the three-phase winding, and inside there is a rotor like this. A rotor will also have the conductors, and these are the terminals A, B, C. These will be connected to the three-phase AC supply to operate this motor, and this is the shaft which is connected to the rotor of this motor. Then once the supply is given, there is a rotating magnetic field produced by the stator windings that will rotate in one direction like this, and whose speed is mentioned as synchronous speed. And that synchronous speed cannot be measured, but the rotor will also rotate because of the induction principle. But that rotor speed can be measured with the help of tachometer, and that rotor speed is represented with capital N like this, and this Ns is the synchronous speed of the motor or magnetic field or stator magnetic field. This cannot be measured, but it can be assessed. So then slip means it is nothing but Ns minus N divided by Ns. Ns is the synchronous speed of the three-phase induction motor, and N is the rotor speed. This is also called the motor speed of the three-phase induction motor, and Ns is the synchronous speed of the stator magnetic field. And power equation is nothing but 2 pi nt divided by 60. In the three-phase induction motor torque slip characteristics, there are two basic regions of operation. One is called the stable region operation, the other is called the non-stable or unstable operation region. So for example, stable region operation means it is like this. Suppose there is a rickshaw without load. So in that case, that is no load. Under this condition, to move it, it doesn't require much torque. So it moves at a high speed. Suppose load is placed in the rickshaw like this. In that case, it cannot be moved at high speed. It has to be moved at low speed. So it requires more torque. That is, should be pulled like this. This is called the stable region operation of the three-phase induction motor example. And coming to the unstable region, in that case, when the load is more, torque is supposed to increase, but torque also reduces. Not only torque, speed also reduces. That is called the unstable region. To understand the torque speed characteristics of the three-phase induction motor, let us see the torque equation is equal to K into S into E2 square divided by R2 square plus S square X2 square. At no load condition, then the speed of the rotor is equal to the synchronous speed. So at no load condition, the speed of the rotor of the three-phase induction motor is approximately equal to the synchronous speed. So the torque will become 0 because slip becomes 0, so torque also becomes 0. This is the slip becomes 0. So once slip becomes 0 means torque also will become 0. So at load, at no load, torque is 0, speed is high, that is ns, and slip is 0. Here, so torque is equal to 0, slip is 0 means this is the first point in the torque slip characteristic of the three-phase induction motor. And let us see then what is going to happen at low slip. What is low slip? Low slip means if the slip of the motor is less than or equal to 5%, then we call that as low slip. Under that condition, in the torque equation, S square x2 square will become very less value, so that it is much less than R2 square, so that this Sx2 whole square can be neglected. Once it is neglected, the torque equation, then the equation will become like this. Torque is equal to K into S into E2 square divided by R2 square. So because E2 square, which is the rotor induced EMF under standstill condition, is constant, and R2 is also constant, K is constant. In that case, torque is directly proportional to S, means the torque slip characteristic under low slip conditions, that is less than 5% slip, the characteristic will become linear, which can be seen here. This is the S is equal to 0, T is equal to 0. Under low slip condition, that is S is less than 5%, the torque slip characteristic will become linear, means slip increases, torque also increases like this. Up to what extent it is from 0 to A. So here A is the maximum torque, this is also called the pull-out torque, and this is the full load torque. The relation between the maximum torque and full load torque is like this. Maximum torque will be approximately equal to 2 times the full load torque. Since torque is directly proportional to S for the low slip conditions, the characteristic is linear like this. When the slip is more than the 5%, then that slip we call as high slip. Under high slip conditions, the denominator in the torque equation will become like this. S square x2 square will be much more than R2 square. So R2 square can be neglected. In that case, torque equation will become like this. K into S into E2 square divided by S square x2 square. So one is going to get cancelled. Then the equation will become like this. K into E2 square divided by S x2 square. Since x2 and E2 are constant, so then multiplication of e2 square by x2 square into k is also again a constant. So the torque will become inversely proportional to the slip, and that is called as nothing but rectangular hyperbola is the characteristic like this. So look at this. This is the region of slip more than the 5%. So the slip is shown, the top slip characteristic is shown with the dotted lines like this. And here there are two regions, that is from here to here, that is this region is called the stable region operation, whereas this dotted region means the left of the thick lines to the right of the thick line characteristic is unstable region. The motor is not supposed to be operated in this region. So if you observe properly, in the linear range, linear characteristic of the three-phase induction motor torque slip characteristic, as the load increases, torque increases, but speed reduces, that is slip increases like this. It continues like this till it reaches the maximum torque like this. After that, if the load is increased, instead of torque increasing, torque reduces like this. But slip continues to increase, means speed continues to decrease up to here like this. So once it reaches this point, the motor stops working, means it comes to standstill condition. And this is the maximum torque at which the slip is called the S is equal to R2 by X2. And this characteristic appears same for both the slip ring type of induction motor and also for the squirrel cage type of induction motor like this. But once it is applied for the slip ring type of induction motor, and if the rotor circuit resistance is varied, its characteristic shape will be same, but get several characteristics for different rotor resistances. So when you look at this, at S is equal to 1, the rotor speed will become 0 because slip is equal to ns minus n divided by ns. So the slip becoming 1 means it happens only when the rotor stops working, means becomes standstill, that is 0, that is ns by ns is 1. So this is the point. Under this condition, the torque available in the motor is called the starting torque. In the unstable region, the characteristic of the start slip characteristic of the three-phase induction motor is a rectangular hyperbola, whereas in the stable region it is linear in nature approximately. Suppose torque slip characteristics are drawn for the slip ring type induction motor by varying the rotor circuit resistance. The characteristics will be like this. This is for one resistance called the R21. This red line indicates the one torque slip characteristic. Suppose the resistance is increased to R22, then the characteristic will become like this. If the resistance is increased to R23, then the characteristic will become like this. Similarly, if the resistance is further increased such that R2 is equal to x to 5, this maximum torque point will become like this. This is S is equal to 1, means rotor speed is 0, and this will become the starting torque. So the starting torque will become highest when R2 is equal to x to 5, that is rotor reactance. So means before this maximum torque condition, this is nothing but a linear characteristic. This is also called the stable operation region. With the high rotor resistance, it is possible to get the stable operation instead of moving to the unstable operation, because the rotor stops here, so there will not be any characteristic further like this. Whereas for other resistors, suppose R21 is taken like this red line. So the characteristic slowly increases like this, that is, as the load increases, torque increases, and also speed decreases from here. So here it is ns, whereas here it goes on reduces. And then after this, if the load is further increased, a rotor torque reduces instead of increasing, and the speed continues to decrease like this. Means for this case, there are two regions of operation. One is called stable operation. In the linear range, it is stable operation, whereas in the non-linear range, the operation of the three-phase induction motor is unstable region. Similarly, for another resistor called the R22, that is this. Up to here, it is stable region, and after this is going to be unstable region. Similarly, for another resistance R23, so up to here it is linear region. After this, it is going to be non-linear region or the unstable region. So if we observe here, the maximum torque is same for the given motor. So look at this, here, 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 everywhere it is same. But the point at which the maximum torque is occurring is different like this. If you want the high starting torque, we have to use the high resistance in the rotor circuit. That can be observed here. So when the R22 is used, that is less resistance is used, the starting torque is only from here to here. If the rotor resistance is increased to R22, the starting torque increases from here to here. That means from here to here. Similarly, if the rotor resistance is further increased, in that case the starting torque increases further, that is from here to here. If the rotor resistance is further increased, so we obtain the starting torque which is also equal to the maximum torque like this. So let us summarize the effect of the rotor resistance on the torque slip characteristic. Maximum torque magnitude is same. With increase in the rotor resistance, maximum torque appears at lower speed, and this starting torque is nothing but maximum torque, that is also equal to pull out torque, happens at R2 is equal to X2. Next, fourth point is, with high rotor resistance, motor can be operated in stable region with high starting torque. Fifth point is with high rotor resistance, high starting torque can be obtained in stable region. So with rotor low resistance, stable region can be maintained, and also unstable region also exists. So we have seen the torque slip characteristic in general. So the same characteristic can also be used for explaining the torque speed characteristic like this. Same characteristic, only thing is at the bottom of the torque slip direction, speed parameter can be mentioned like this. When S is equal to 0 means the speed of the rotor is ns, that is synchronous speed. When S is equal to 1 means the rotor speed is equal to 0, means from 0 to ns, that is the maximum speed which can be obtained. The graph that we get between this torque and this speed is called the torque speed characteristic, and it is only one characteristic for the squirrel cage induction motor, whereas for the slip ring type of induction motor, torque speed characteristics can be obtained with different rotor circuit resistances like this. So these are the characteristics for different rotor resistance values in the slip ring type of induction motor. This is the speed. This is 0 and this is ns. So same characteristic, that is torque versus slip, you can draw like this, and then here at the bottom of the slip parameter, draw the speed parameter like this and put here 0 and here it is ns. So this explains the torque speed characteristic. So at high speed the torque is 0, whereas at low speed, that is 0 speed, the starting torque is decided by the rotor resistance like this. For low resistance, this is the starting torque. For further resistance increased, the starting torque will increase. Further resistance increasing in the rotor circuit increases starting torque like this. So here also it can be observed that maximum torque for a given motor is a constant. Its position will change, but its magnitude remains same like this. Similarly, we also see the three modes of the operation of the three-phase induction motor using the torque slip characteristic like this. So we have seen the torque slip characteristic, that is here, this is the slip S is equal to 1, that is standstill condition of the rotor.
Concerned, resistor depends on
Now let us see how the three-phase induction motor operates in three different modes, that is motoring mode, generating mode and braking mode, depending upon the direction of rotation and the speed of the rotor with respect to the stator magnetic field speed. So we have seen the torque slip characteristic. This is the torque axis, this is the slip axis, and this is the speed axis. Slip is from right to left, and whereas speed is from left to right like this. So this is the 0 speed, and this is the rotor synchronous speed, and this is the rotor speed which is equal to ns but in the backward direction. So when the rotor speed is less than the synchronous speed, that is synchronous speed is more than the rotor speed, that is in this region, that is s is equal to 0 to 1, this is S is equal to 0 and this is S is equal to 1. The operation of the three-phase induction motor, we call it as motor operation or motoring mode operation, and this is the linear characteristic, and this is the full load operating point up to which it can be safely operated. Beyond this, it can be operated up to here, but only for a short duration. But after this will become unstable region like this. Suppose the rotor speed is more than the synchronous speed. In that case, it is possible if the rotor is coupled to a external motor shaft such that its rotor speed increases to more than the synchronous speed of the slip ring induction motor or motor. In that case, the slip will become like this: ns minus n divided by ns, because n is more than the ns. So here the slip will become negative, that is less than 0. In that case, that motor operation is called in the generating mode. So to operate the three-phase induction motor or three-phase induction generator, three-phase capacitor bank should be connected across the stator windings to provide the reactive power. Similarly, if the stator terminals, means three-phase supply, two phases are interchanged, in that case the stator magnetic field direction changes. At the same time, the rotor also changes its direction from one direction to the other direction. At one point, it becomes 0 before it moves to the other direction, and that is the point at where the supply should be cut off. That is called the braking region. From here to here, it is braking region, and slip is more than 1. So maximum possibility is only 2. So we can say here, for braking mode the slip is more than 1, whereas for motoring mode slip is between 1 and 0. For generating mode the slip is less than 0. So depending upon the necessity, we apply braking mode or motoring mode or generating mode, and under these cases also stable operation is required. So let me summarize once. We have seen what is the torque speed characteristic of the three-phase induction motor, and we have seen what is the torque slip characteristic of the three-phase induction motor, and we saw that what is the difference between the squirrel cage induction motor and the slip ring induction motor. For the squirrel cage type of induction motor, there is only one torque slip characteristic, whereas for the slip ring induction motor, there are different types of the torque slip characteristic. For all these three-phase induction motor torque slip characteristics, the motor should be operated in the stable region, that is thick line area like this, and it is preferably is to be operated at full load condition. So full load torque means it is the torque at which it can be operated without exceeding the temperature limits. If the torque is the load is increased, torque can be increased, and it can reach up to maximum torque like this. And this region of operation from C to A can be allowed only for shorter duration, and beyond this point A, that is beyond the stable operation, the motor should not be operated. So the motor should be always should be operated in the stable region for useful application. And we also saw the how the torque speed varies like this. This is the speed direction, this is the slip direction. And we also seen what is starting torque, And we also observe, so what is the maximum torque for a given motor, that it is almost it's constant for a given motor, but only thing is its maximum torque occurring point can be changed by increasing the rotor circuit resistance